Hello, in this lecture, we briefly discuss descriptive statistics. Descriptive statistics are some measures or values that we use to describe or characterize a variable. There are different kinds of descriptive statistics, including measures of central tendencies, measures of dispersions, and measures of shapes. Let's take a look at each one of them in turn. First, let's discuss the measures of a central tendency. Central tendency refer to the measures that give us a sense of a central place or typical value of a variable. The most important measure of central tendency is the average or the mean of a variable. I'd like to make a distinction here. We normally use a Greek letter to represent the descriptive statistics for the statistical population and use a English letter to represent the descriptive statistics for a sample. Here I give a formula for the sample mean. As you can tell that this is an English letter that represents the sample mean. There on the right hand side of this formula, on the top we have this Greek letter sigma, and that means find the sum, find find summation over all the different values of variable x. X subscribe I run from number 1 all the way through number n. N means the number of cases, a number of observations for this variable. You may have number 1, number 2, number 3 until number n. Okay, and so I will run from 1 through n. So you have x sub 1, x sub 2, x sub 3, so on and so forth. All represent the values of variable for first case, second case, until the case number n. And for all these values of variable x, you find sum and divided by the total number of observations. That would give you arithmetic average or the mean. If you write out this succinct equation, that's what it means. Every single value of variable y, find the sum, find summation, and divided by n. Okay, so this is a sample formula, but for a population formula of the mean, it should be the same, except that there should be a mu here, but we show a sample formula. Characteristics of the mean. When we come to calculate the mean, we use all the values in the variable. So every single value in the variable should be brought to the formula to calculate the mean. So if you have some values in the variable that is extremely large or extremely small, they could disproportionately influence the outcome of the calculation of the mean. So those extreme values sometimes are called outliers. So the mean could be profoundly influenced by outliers, especially extreme outliers. And also mean can take on an unrealistic value. For example, if you want to calculate the number of children, average number of children in a family, and you may come up with 3.59, and the children cannot take this value with decimal, but that's the result of calculation. In this case, it is unrealistic. Okay. Now let's show an example of how do we calculate a mean by using that formula, and look at this is how the formula is used. You have this formula itself. You plug in the numbers divided by the total number of cases, that give you the mean. And to show how the extreme value may have impact on the outcome of the mean. And if you have this extremely small value, so this is 3 value to begin with. If this value become extremely small, and that would have impact on outcome, the outcome become very small. Then if you have an extremely large value, that how it would affect the outcome of the calculation of the mean. So that's the mean is a value. Since you have to bring in every single case into the calculation, those extremely small or extremely large value may profoundly affect the result of calculation. So then we have the notions of mean center and geographical center. The mean center expresses the means of multiple variables at the same time. Let me just go to this the other slide here. If we have let's say 3 variables, x, y, and z, and we calculate the mean for all 3 variables altogether, these 3 values, 11.7 is the mean for variable x, 23.3 is the mean for variable y, 6 is the mean for variable z. These 3 values together is called the mean center. So mean center refers to the means of several variables. For several variables. In a 3-dimensional space, you can really get a sense of this point. Okay, this point. This point corresponds to the mean x at this x-axis. Y 23.3 on this point, and the mean value is 6 at this point. So this point simultaneously express the means of the 3 variables x, y, and z. So therefore this point is called the mean center. The mean center. We use this 3-dimensional space to show the mean center. But here the mean center is simply 11.7, 23.3, and 6 together. Okay. When we have two variables, these 2 numbers together is also called a mean center, because this is the means of 2 variables. But now, if these 2 variables has a special meaning, that is, for x, it represents the geographical distance east-west direction. Y represents the distance north and south direction. They could be measured in miles. They could also be measured by latitude, longitude. Doesn't matter, as long as that these are geographical measures. This mean center has a special name: geographical center. Geographical center. So we can define geographic center is a special case of the mean center with 2 distance variables. Okay. So we skip this one. Okay. The median. Median is a value in a data set that divides the number of cases in a data set into 2 equal halves. Above the median and below the median, you have an equal number of cases. How do you determine the median? 3 steps. First, you arrange the cases according to their values, ascending order or descending order, either way. Second step, you find the value of the cases in the middle. Okay, if you have an odd number of cases. In case that you have an even number of cases, you take the average of the middle 2 values to obtain the median. Let's show an example here. Okay. we have a data set x. To find the median, you rearrange variable x in an ascending order. The one value in the middle is the median when you have an odd number of cases. In this case, we have 5 cases in the variable. So the variable in the middle, the value in the middle, 7.1, is the median. It divides the variable into 2 equal half. 2 cases below 7.1, 2 cases above 7.1. But in case that you have an even number of cases, you rearrange everything in ascending order or descending order, and you take the middle 2 values, find the mean between the 2 middle values. 7.55 in this case is the mean between 7.1 and 8.0. So thus 7.5 would be the median. It would occur between 7.1 and 8.0. Okay. So this value divide dataset into 2 equal half. Below 7.55 you have 1, 2, 3 cases. Above 7.55 you have 3 cases. Okay, this is median. Characteristics of the median: not affected by extreme values. Not all values are used in calculation. Median is the 50 percentile of a variable. As you can see from previous examples, when we come to calculate to determine the medians, we really do not use all the values. In this case, we decide the median just by using the value of the 2 middle cases. Now let's see how the median is not affected by the extreme value. This is the data set here, and the 6.7 is the median. If we introduce extremely small value and extremely large value, the median is still 6.7. It's not impacted by the extreme value in the data set. Median is the 50th percentile of a variable. This means that below 7.55 there are 50% of cases in the variable. In this case, below 7.1 there are 50% of cases in the variable. So that is 50th percentile. The mode. The mode is defined as the most frequently occurring categories or value in a variable. Okay. Let's look at this example here. In this data set, which value has the highest frequencies of occurring? 7.1 occurred 1 time, 5.5 occurred 1 time, only 8.0 occurred 2 times. The highest frequency, therefore the mode of this data set is 8.0. Now, if we have a categorical, variable, you could have people vote for Democrats. You can see how many people vote for Democrats, how many people vote for the Republican. 1, 2, 3, 5 people vote for Democratic Party, and 3 people or 4 people vote for Republican Party. Therefore, Democrats is the mode in this data set. Okay. So that is a case when we have only one mode in one variable. You have a one value or one category has the single highest frequency of occurring. But also there are times a data set may have 2 modes, even 3 modes. That's why you have a bimodal data set, trimodal data set, so on, so forth, multimodal data set. If you look at this example for this data set, I see color balls, red ball, green ball, blue ball, green ball, yellow ball, red ball, red ball, blue ball, blue ball. Therefore, you can see red occur 3 times, and green ball occur 3 times, and the blue ball occur 3 times. Therefore, this data set had 3 modes, red, green, and blue. Okay. Characteristics of the mode. The mode does not need to be near the center of middle of the range. For example, you could have a data set that reads like this: 2, 2, 2, 3, 4, 5. 2, 2, 2, 3, 4, 5. In this data set, 2 occur 3 times. 3, 4, 5 occur 1 time. Therefore, for this data set, 2 is the mode, most frequently occurring value. But 2 occurred at the edge, at one end of the distribution. In 2, 3, 4, 5, 2 is the smallest value, not in the middle. So that is what this first statement said. The mode does not need to be near the center or middle of the range. Also, mode can take on more than one value. We just discussed one dataset could have more than one mode. Okay, and the mode is commonly used for categorical data or less precisely measured values. For example, the names, how many people have the name John, and what is the most common name in the country? Is that the Jennifer? Is that the Smith? That is categorical variable. And also, a mode is suitable for distributions where the data are clusters about the multiple points. As I said earlier on, you could have a multi-model data set. When that happened, and you could use a mode to describe the pattern of distribution. Measures of dispersion. Okay, measures of central tendency give us a sense of the typical values of a data set of a variable, but it's not enough. Look at this. We have 2 examples here. In both cases, we have 3 individuals. They all earn their income. Okay, $49, $50, $51. Let's say per hour, per day. And another data set, 3 individuals. One is $1, the other is $50, another is $99. For both data sets, the average, the means are the same. The means are the same. The mean is 50 for both data sets. The mean is 50 for both data sets. But you can see, but for the first case, you'll find a very small gap between individuals. As a result, you can imagine that the 3 individuals are kind of happy. They earn similar amount of income. So they don't really feel much difference among the 3 of them. But for the second data set, each individual earns extremely different level of income. Although the average income among the 3 people is the same between the 2 data sets, but amount of discrepancy among individuals in terms of income level is extremely different. The second data set indicates a very large rich-poor gap, and the first one indicates very kind of high level of equality. So therefore, only look at the average value, look at the mean is not enough. We need to measure that describe this gap here, the small gap and the large gap, a large gap. So that is reason we try to have measures of dispersion. Now, one measure of dispersion is variance. Now, this is the formula we use to calculate population variance. As we said, that this is a Greek letter. Sigma squared means variance. This is the formula we use to calculate population variance. Here, mu is the means of the statistical population. So in this formula, you need to use a mean, since this is a population variance formula. The mean is also the population mean. Okay. Then the difference between x and the mean is called the deviation. It's called the deviation. Deviation is the difference between individual values and the mean. When you calculate the variance, you need to calculate the deviation first. Then for each deviation, deviation is calculated by using the value for each case minus the mean. This deviation, you need to square it. Then you find the sum of deviations for all cases in a data set. And this big sum divided by the number of cases. Okay. So this is the formula we use to calculate the population variance. In most cases, we're not going to be dealing with population. So we just leave this formula here, and we only use it on some occasions, but in most cases we use a different formula, use the sample formula to calculate variance. And but now we introduce this formula, and there will be times that we're going to use this formula, but most of the time we'll be using the sample variance formula to calculate a sample variance. Okay. Another measure of dispersion is standard deviation. Obviously, in this case, is population standard deviation. Population standard deviation is simply the square root of population variance. As you can see, that this formula is very similar to the previous formula, except that for the previous formula, you take square root, then you obtain the population standard deviation. Again, in most of the cases, we will be calculating sample standard deviation, and but now we introduce this population standard deviation formula here. Okay. So often we calculate the sample variance and the sample standard deviation. Between the population variance and the sample variance, between the population standard deviation and the sample standard deviation, there's only one difference here. The main difference here is at the bottom. Is at the denominator. We use n-1 to divide it into that big sum. We do not use number of cases. Why? We explain this later on. But right now, just remember this formula. The rest of the formula looks similar to the population formula, except at the bottom we use n-1 instead of n. Same can be said about the sample standard deviation. Another minor difference here is that we do not use the mu here. We do not use a population mean. Since if you do not have the population mean, you just have to use a sample mean and bring the sample mean into the formula to calculate the sample variance and the sample standard deviation. Okay. We're going to have an in-class activity where you're going to practice how to calculate variance and standard deviation for a sample. Okay.